When you look at the stars, you're seeing a fraction of the story. In the deep void of space, massive, violent collisions are occurring right now that produce no flash and leave no trail of light. Our understanding of the cosmos has historically relied on capturing light. We build instruments like the James Webb Space Telescope with enormous golden mirrors to gather ancient photons from the edge of the universe. But when the most dense objects in existence, black holes, collide, they are completely dark. Instead of light, they release gravitational waves, physical ripples in the geometry of space itself. Relying exclusively on light-based telescopes means humanity is effectively blind to the most energetic events in the cosmos. The Laser Interferometer Gravitational Wave Observatory, or LIGO, serves as our ears to the universe. It listens for signals that traditional telescopes could never catch. Detecting these waves requires precision on a scale that defies intuition. By the time a ripple reaches Earth, it distorts space by a distance thousands of times smaller than a single proton. LIGO is so sensitive that it records everything: the vibration of a passing truck, the crash of distant ocean waves, and even its own microscopic heat. Building the detector was a feat of engineering, but the true scientific victory lies in isolating an infinitesimal cosmic whisper from this deafening mountain of earthly noise. To find that signal, we have to know its exact shape. In 1915, Albert Einstein's field equations predicted that massive, accelerating objects would physically squeeze and stretch the universe as they moved. This distortion happens in specific, predictable directions called polarization. This chart illustrates H+ polarization. As a wave passes, space squeezes vertically while stretching horizontally, behaving much like a water balloon being pressed from the top. This second graph shows H-cross polarization, where that same stretching and squeezing occurs on a diagonal axis. If you've ever seen a sci-fi movie like Interstellar, you can visualize it: a three-dimensional wave of space-time bending and flexing as it passes right through you. While physicists understand the math behind these shapes, no human can process the sheer volume of chaotic data required to identify them in real time. This is where artificial intelligence becomes essential. Researchers use convolutional neural networks to scan the massive data streams generated during LIGO's current observing runs. By training on thousands of simulated collisions, the AI learns to ignore the static and identify the distinct spiraling chirp of a real gravitational wave. This 3D graph tracks machine learning performance over recent years, showing a steady decline in the false positive rate. AI separates cosmic events from local interference in milliseconds, allowing scientists to flag anomalies the moment they hit the detector. AI serves as a high-speed decryption engine, translating LIGO's raw data into clear signals of the universe's most violent events. AI-driven analysis has started to uncover exotic cosmic anomalies that defy standard expectations. This infographic summarizes GW230529, a rare collision between a neutron star and a black hole. Its primary object falls into an empty region of physics known as the lower mass gap, forcing us to rethink the life cycles of the largest stars. Without the unbiased eye of an algorithm, these outliers would likely be lost in the noise of more common events. As we look toward next-generation detectors like Cosmic Explorer, the data streams will become so massive that AI will be our only way to make sense of the results. We have moved beyond merely looking at the stars. We are now experiencing the physical vibrations of reality. The dark space between the stars is not truly silent. It constantly rings like a bell from the echoes of the universe's most powerful collisions. What other secrets do you think are hidden in the dark? Share your thoughts below and subscribe as we continue to listen to the whispers of the cosmos.